Hope you're all doing great. This is part 2 video, metal carbonyls, which includes the structure and shape of polynuclear metal carbonyls. In this first we go for dimanganese Deca carbonyl. So here if we see the structure of dimanganese Deca carbonyl in solid state, it shows octahedral structure. So here we have two manganese atoms bonded with 10 carbonyl groups. In this, each manganese is attached to or bonded with 5 carbonyl groups, and the sixth bond is in between two manganese atoms. So we know that the atomic number of manganese is 25 and it is written as organ 3d5 and 4s2. So here manganese electronic configuration, we can write it in the form 3d with 5 unpaired electrons 3d5 and 4s is 2 and 4p is totally empty, that is vacant orbitals. All the three are vacant. So here in the presence of carbonyl groups or in the presence of ligands, rearrangement takes place. That means the electrons from 4s orbital are rearranged in 3d orbital so that pairing occurs and we get 3 paired electrons in 3d orbital and 1 single electron. And totally this happens for the second Mn atom also. So in Mn2 atom the same will occur, that means rearrangement takes place. So the 3d orbital is with 3 paired electrons and 1 single electron, and 4s is vacant. This is 3d, and 4p 1 is totally empty. And now we see we take coming to Mn1 atom, we have 5 carbon, it is bonded with 5 carbonyl groups. Here the empty orbitals, we have totally 5 empty orbitals, that means 1 3d and 1 4s and 3 4p orbitals. These vacant orbitals merge together and gives rise to D2 sp3 hybrid orbitals. So here one d orbital having unpaired electron and the vacant d orbital, 1 4s and 3 4p orbitals, they merge together and gives rise to D2 sp3 hybridization. So we'll get 6 D2 sp3 hybrid orbitals. D2, so we get 6 D2 sp3 hybrid orbitals. Now we know that manganese is bonded with 5 carbonyl groups. Here we have 5 empty orbitals, so that these 5 carbonyl groups donate electron pairs to these 5 empty orbitals and forms a dative bond. Okay, and here also these 6 orbitals, that means 2 d orbitals from 3d and 1 4s and 3 4p orbitals, they merge together and gives rise to D2 sp3 hybridization. Now again we have 5 carbonyl groups, they donate electrons to this and forms a dative bond. So we can show like this, electron pairs. Here also like this, okay, and the one unpaired electron from both the manganese atoms, they too gets paired up and gives one metal bond. That means here we can see a bond between manganese 1 and manganese 2 atom. In this way, here the structure of manganese is seen like this with 2 octahedrons, each with manganese atom at the center and 4 carbonyl groups like this. And here this manganese is attached to the second manganese atom and another octahedron is like this as shown in the figure. So here we can see clearly that each manganese atom is bonded with 5 carbonyl groups. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we can see one metal-metal bond between two manganese atoms. Okay. So from this we can conclude this dimanganese decacarbonyl, it shows 10 terminal carbonyl groups, 10 terminal carbonyl groups and one metal-metal bond. Here no bridging ligands are seen in this dimanganese decacarbonyl, as all the electrons in the orbitals are paired up. This shows diamagnetic nature. Diamagnetic nature. Also we know that here 10 terminal carbonyl groups and one metal-metal bond. Also here we have in each manganese atom one unpaired electron is present, but these two unpaired electrons gets paired up with each other. So we can see no unpaired electrons in this dimanganese decacarbonyl. So the metal carbonyl shows diamagnetic structure. So this is all about the structure and shape of dimanganese decacarbonyl. And the next one we see from iron metal carbonyls. Okay. So the second one is iron Penta carbonyl. So this is FeCO5. So electron diffraction and X-ray studies have concluded that this iron pentacarbonyl has a shape of regular trigonal bipyramidal structure. Regular trigonal bipyramidal structure. Okay, so this we can explain by seeing the bond structure of metal carbonyl. So we know that iron, its atomic number is 26, and in the ground state configuration is written as organ 3d6 4s2. Organ 3d6 4s2. In excited state, it can be written as, and the ground state configuration we can write like this. Okay. So 3d6, 1, 2, 3, 4, 5 and 6th electron, and 4s is with 2 and 4p is 0 vacant. 3d is with 6. Okay, so this is ground state configuration. 3d orbital with 6 electrons and 1 is paired, and 4s with 2 electrons and 4p is totally vacant. Coming to excited state, the configuration, there is little change in the configuration. That is, in excited state, one electron from s orbital gets excited to 4p orbital. So that rearrangement takes place as shown here. So 3d 6, 1, 2, 3, 4, 5, 6 and 4s 1 electron, and 4p it gets 1 electron. So this is how rearrangement takes place. Now iron, totally we have 6 unpaired electrons, 4 from 3d, 1 from 4s and 1 from 4p orbitals. Totally we have 6 unpaired electrons through the rearrangement. Okay, So 4 in 3D, 1 in 4s and the other in 4p. So in the formation of iron pentacarbonyl, these three last 5 orbitals, that means 3 from here, 1 and 3D, 1 from 3D orbitals. So 1 3D, 1 4s and 3 4p empty orbitals, okay, or having 1 electron intermixed to give dsp3 hybrid orbitals. Understood? So here it undergoes dsp3 hybrid orbitals. So 1 orbital from 3D, 1 from 4s and 3 from 4p having unpaired as well as vacant orbitals. They intermix and gives rise to 5 dsp3 hybrid orbitals. Okay, 5 dsp3 hybrid orbitals. Now we can see, and also we have pure orbitals from 3D also. Now we can see the bond formation. The bond structure of iron pentacarbonyl can be seen like this. So Fe 26 and organ 18, and the remaining we can show like this. Okay, so here 4p1, 4s1 and 3d with 6, 4, 5 and 6, here 1 electron and here 1 electron. So this is showing dsp3 hybridization, and also we have 5 carbonyl groups, 5 carbonyl groups that are attached with iron. So these 5 carbonyls come like this, and these 2 empty orbitals are there in 4p orbital. So these 2 carbonyl groups, they donate electron pair to these empty orbitals or vacant orbitals from 4p and forms a dative bond. Okay, now we have another 3 dsp3 hybrid orbitals are left, and here these electrons, they take up, so each carbonyl having 2 electrons, and this will take up this electron, and this will take up this electron, and this will take up this electron, and forms a sigma bond with carbonyl groups. Understand? So here vacant orbitals, they'll accommodate the electrons donated from carbonyl group and forms a dative bond. And so here these 2 dsp3 vacant hybrid orbitals are occupied with electrons donated from carbonyl groups and forms dative bonds, while other 3 dsp3 hybrid orbitals, that is 1 from 4p, 1 from 4s and the other from 3d orbital, these 3 hybridized dsp3 orbitals having single electrons take up 1 electron from carbon monoxide group and forms a sigma bonds. And we have a single electron left here in these 3 carbonyl groups, and these get paired up with the pure 3D orbitals, and these pair up with these unpaired electron left in the carbon monoxide groups and forms a pi bond. Okay, understood? Here we can see 3 types of bonds. One is dative bond, that is formed out of the 5 dsp3 hybrid orbitals. The 2 vacant orbitals forms dative bonds, and 1 4p and 1 4s and 1 3d orbital having dsp3 hybrid orbitals with single electrons, they pair up with the electron from carbon monoxide molecule and forms a sigma bond, while these 3 pure 3d orbitals, they pair up with the other electron left with carbon monoxide molecules and forms a pi bond. This is how bond formation takes place between carbonyl groups and the metal atom. Okay, so and here we see dsp3 hybridization. Okay, and the structure of this iron pentacarbonyl is trigonal bipyramidal structure. Trigonal bipyramidal pyramidal structure. Okay, so this is how the bond formation takes place in iron penta carbonyl molecule. And next we can see another iron carbonyl, that is from iron Inia carbonyl. It is having 9 carbonyl groups attached with 2 metal atoms. Okay, so the structure I am drawing here for iron pentacarbonyl. So it's with 2 dative bonds. So this is the bond structure of iron pentacarbonyl. Okay, here these arrows indicates dative bonds with iron. Okay, so we get trigonal bipyramidal structure with 5 carbonyls bonded with iron like this. Okay, here as all these are paired up with carbon monoxide molecules, it shows diamagnetic structure. So next we see the structure of iron Inia carbonyl. So iron Inia carbonyl, it is Fe2CO9, 2 iron atoms bonded with 9 carbon monoxide groups. Okay, it shows symmetrical structure. Okay, and this can be understood easily from the bond formations between iron and carbonyl groups. Okay, so iron atomic number 26 and configuration is organ 3d6 4s2. So it is seen like this. So 3d6 4s2 and 4p0. So 1 2 3 4 5 and 6 1 2 electrons from 4s orbitals. And here the bond structure of iron Inia carbonyl shows 2 types of carbonyl groups. Here we get 2 types of carbonyl groups. That is, one is bridging carbonyl groups, and second thing is terminal carbonyl groups. Okay, so bridging carbonyls we can see 3, and terminal carbonyls 6, they are 6 in number. Okay, so this bridging carbonyls, they form bonds with both Fe1 atom and Fe2 atom. This can be easily understood by drawing the bond formation or bond structure of iron Inia carbonyl. We see the electronic configuration of Fe1 atom. So here also rearrangement takes place in the presence of ligands. So in this Fe1, in the presence of ligands, rearrangement of electrons takes place, and 1 electron from 4s orbital goes to 3d orbital, and we get 4, 5, 6 and 7 here single electron. Okay, and 4p orbital is vacant, 4p0, 4s1 and 3d will get 7 electrons, 2 paired electrons and 3 single electrons are present in 3d orbital. Okay, here we have only 3d 6 electrons and 4s with 2 electrons. In the presence of ligands, rearrangement takes place so that 1 electron from s orbital goes to 3d orbital, and so that we get 2 paired electrons and 3 unpaired electrons from 3d orbital and 1 unpaired electron from 4s orbital, and 4p is totally vacant. Now 2 3d orbitals, 1 4s orbital and these 3 4p vacant orbitals, they merge together, intermix and gives rise to D2sp3 hybridization. D2sp3 hybridization. This also happens in Fe2 atom like this. So here I am writing Fe2 configuration. So this is 4p0 and 4s1 and 3d 1, 2, 3, 4, 5, 6 and 7. Okay, so here we have 2 3d orbitals and 1 s orbital and 3 4p orbitals undergo D2sp3 hybridization. Okay, so here out of 9 carbonyl groups, 3 carbonyl groups, they donate electrons to these vacant orbitals and forms dative bonds like this. And so here out of 9, 6 carbonyl groups are bonded with 3 D2sp3 vacant orbitals. Okay, and we are left with other 3 orbitals of D2sp3 hybrid orbitals, and we have another 3 CO molecules. These are bridging carbonyl groups. These are bridging carbonyl groups. Carbonyl groups. These are terminal carbonyl groups. So these 3 bridging carbonyl groups, they donate their electron pairs to both Fe1 atom and Fe2 atom. Okay, so these have electron pairs like this. So in this, 1 electron goes here, the other and the other, and the left unpaired electrons will be bonded to, okay, CO, CO, CO. Okay, so these bridging carbonyl groups, we have 3 carbonyl groups which give electron pair here, 1 electron, 1 electron, and here also 1 electron goes here, and in this way they bond form with both Fe1 and Fe2. Okay, bridging carbonyl groups, they give their electron pair to Fe1 as well as Fe2. Okay, and the other electron left in Fe2 and Fe1 and Fe2, they both get paired up and forms one metal-metal bond between Fe1 and Fe2. Understand? So here the 2 D2sp3 hybrid orbitals, they got paired up. So here the bridging carbonyl groups donate their electrons to Fe1 as well as Fe2. Okay, and the pure 3d orbital with single unpaired electron from Fe1 atom and Fe2 atom, they got paired up by giving one metal-metal bond between Fe1 and Fe2. Okay, so with this we know that the structure and shape of iron Inia carbonyl consists of 2 types of carbonyl groups, that is terminal carbonyl groups and bridging carbonyl groups. terminal carbonyl groups donate their electrons to three vacant D2sp3 hybrid orbitals and forms a dative bonds, while the three bridging carbonyl groups shared their electron pairs to both Fe1 and Fe2, giving three bridge bonds, and the unpaired electron that is left in pure 3D orbital is paired up from Fe1 to Fe2, giving 1 mm bond. So totally we have terminal carbonyl groups and 3 bridged carbonyl groups and 1 metal bond. Okay, now I'll draw the structure of Fe like this. So 1 metal bond, and we have 3 terminal groups, and here 3 carbonyl groups like this, bridged carbonyl groups. Like this. So this is the bond structure of Fe2CO9. This is called as iron Inia carbonyl. Once again we'll go through the structure. It shows symmetrical structure, and iron atomic number is 26. So this is a configuration of iron atom in the ground state, and in this structure we have 2 types of carbonyl groups. One is bridged carbonyl group and the other is terminal carbonyl group. Okay, so here Fe1 and Fe2 we have metal atoms, and in the presence of ligands, rearrangement of electrons takes place. So 1 electron from s orbital goes to 3D orbital. So the 3D will have 7 electrons with 2 paired electrons and 3 unpaired electrons. This is same for both the atoms, and here these 2 3D orbitals, 1 4s and 3 4p vacant orbitals, get mixed up and merge and forms D2 and forms 6 D2sp3 hybrid orbitals, giving D2sp3 hybridization. So these 3 D2sp3 vacant orbitals gets accommodated with the electrons donated by the terminal carbonyl groups and forms a dative bond, and the other 3 D2sp3 hybrid orbitals having single electron, they got paired up with bridged carbonyl groups in both the atoms, and the other unpaired electron in the pure 3D orbital from Fe1 and Fe2 paired up and gives 1 metal bond between Fe and Fe. Okay, so that we have 6 terminal carbonyl groups, 3 bridged carbonyl groups, and 1 metal bond between iron and iron. And show this is a structure of Fe2CO9. Okay, so this is, and here also we have all the orbitals are filled up with paired electrons. So this is diamagnetic in nature. Diamagnetic in nature. Okay, so thank you for watching, and in my next video I'll upload few bits which will be useful for common entrance examinations. Thank you.